search. Haven't done a video in a while since I had spring break, but good to be back. This problem is interesting because I just had an interview and they gave me word search 2, which was a hard problem. I can show you that here. And so word search shouldn't be as tough. Hopefully it'll be easier, but I also did not run my code for that word search 2. So let's see if I can do this. I have done this before, but doesn't mean I remember it. Okay, so you're given an n by n grid of characters board and a string word, return true if the word exists in the grid, and as in return false if it's not. The word can be constructed from letters of sequentially adjacent cells where adjacent cells are horizontally or vertically neighboring. The same cell may not be used more than once. Okay. So input board m by n. Let's just 2D array of characters. 2D array, 2D board. Define word in. Word was a string. Word defined cannot not guaranteed to be in board. Output Boolean indicating if word is in word search. So a couple of notes that we have. Move horizontally or vertically. Cannot visit cell again, so can only use cell once. And I think with that, that's basically it in terms of constraints here. So this can be true if word in word search in board, sorry. False if not. Okay. So this is definitely a backtracking problem, right? So where we have to try through every option. I mean, if I were to do it myself, the way you solve a word search problem yourself is you go to every position and you see, okay, is that position the beginning letter of the string? So I mean, this is a bad example. Let's do this. So the word we have is C, and we start with A. So A, we start with S. The A is not the first character. Sorry. The A is not the first character of the first word. So that's not possible. Same for B, C, E, S. So now we hit S, and we see, okay, S is it. So let's go to its neighbors, A, F, and A. Are those the second characters of S? No. Okay. So then this path is not valid. So we go back to F, C, and then S. This is a valid. We go every option. Let's try this E first. E is also a valid option, SE. So then we try all the options here. This is out of bounds, this is out of bounds. So that should break our potential paths there. This C is not possible. So we don't do this. And we exhaust all the options in this E. So we go back to this S and we try this C. That's not possible. So we go down to this C. That's possible. That's possible. And the second we see, the moment you find the word, return true. Okay. So what's the backtracking logic? So I think let's skip the backtracking algorithm per se. The logic is for every row. Let's see this. For every column, if this cell is the first character in C, in word, run. We can remove this abstraction. We can just run backtracking on I plus 1. On just I. On index 1. Right. We can avoid this. We can handle this in the backtracking. It'd be easier. I mean, it'd be cleaner logic, but anyways. So argument for backtracking is row, column, and index in word. So a couple of cases we have. So if index is out of bound, is past word length, return true. Now when backtracking, if this returns true, return true, and then return false here, right? So we have to try every combination. If this backtracking ever returns true, that means we found a path, return true, and if all exhaust, return false. Okay, so index is passed, we return true. If row or column is out of bounds, return false, right? And then, so we also need to keep track of this one. We can't visit a cell again. So right now I'll have set where visited cells equal to this. We can optimize, or we can just use a board as a marker for this, but for now we'll have this for now, and then we'll have the set for now, and I can explain the optimization later. But if row column is in visited cells, return false, right? So what is it? This row column is always going to be unique. There's not going to be multiple instances of row and column, so it's fine if it's in visited cells. I mean, we visit again, so we don't want to continue that path, right? If we do SEC and then back to SE, if there's 3 E's, we go back to this E. We don't want to do that, right? Okay. So this means that this row and column is valid, and we are not completed with finding the word. So, and then another check is if board at row column is not equal to word at index, return false. Right, because we can guarantee this index is valid because we checked this here. We guarantee this will be a valid check because of this, and it's not repeated. And so if this is false, then also okay. So now that we guarantee at this point index is valid, row and call are within bounds, and index. Then for this, so for every -1, how do I do this in the alternate? Because the most brute force way is I do go up, go down, go left, go right. But I'm trying to think, is there like a way I can do optimization where this is +1, -1, for x delta and y delta in we have, so from here we want to go, you want your row to be x to be same but y to be 1, you want your this to be -1, -1 0 and 1 0, right? Okay, for all this backtrack and row plus xd, call plus yd, and index +1. So if this returns true, return true, and then if this doesn't return false, then return false here, right? Okay, so let's implement this. So visited set, backtracking, we'll do row call index, we'll implement this later. Implement later. And then for row in length of board, for column in length board 0, I'm gonna guarantee this board will be, yeah, okay, I'm guaranteed this will be a valid board. I don't have to verify this board is And then from here, this, I can try backtracking. This is spelled wrong. Backtracking, row column 0, return true. Index, I think the word, I mean, it can just be equals to, and it won't go out of bounds, but go ahead and equal to, I like putting in general. If row less than 0, row greater than, make the board, column less than 0, or column row greater than equal to, and equal to length of board 0, return false. Okay. If row column so one thing I need to do is once this is validated, I need to add this. So add row call to visited, and then remove row column, sorry, from visited. Okay. And then if board at row, not the word at index false, and then from there for x delta, y delta in this, so just copy this. If backtracking plus x plus d and call of y plus d, index plus 1, return true, return false. This works. Let's run it. Well, actually, okay, let me let me actually go through an example here. Oh wait, oh shoot, I see. This is a Bladen. Okay, so visited cells, add row column, remove row column. Okay, now, so for everything, so we start at this A, and index is always 0. Index is, this is not true, this is not true, this is fine, so it passes here. There's nothing in visited, so it's fine. This returns false, so that's fine. Skips. B, same thing here. C, C, E, and then S. So this is passes, right? So then it goes to here. You add this S here, then it goes up here. This is false, so it returns false here, and then removes it. Goes to the next one, adds visited cell here. I could move this up here, but I'll make it. I can move up, down. But anyways, A is here. Backtracking this out, that's obviously fails here, and then removes, and that's all fine. Okay, FC, and then we have this S here. This all passes here, and so out of bounds, if it goes up, this is up. This is true, so it goes to the next one. It goes to the next one here, but then out of bounds return this returns false. This returns false. This should return false because it's visiting another cell. Here, this return false, so this should return false and removes this S, but then it visits S here again. Check this path, that it fails, goes here, and then I think it should run. So let's run it. Oh, for in range of like the board. Too much Python syntax. Alright. Will this take too long? Let's see. Solid. There you go. Not the most optimal, but let's see. If I move this up here, honestly, this runtime are not always consistent. Okay, so the optimization I was saying is the optimization I was thinking about is rather than having a visited set, we can use the board itself. So rather than adding to visited cells, we just set the board at this row as like some character, either a character that is not an ASCII character, right? Only uppercase, lowercase, uppercase character. So it can be hashtag or something like that. So that'll indicate that it's visited, and then once we're done with this, we remove it because we don't care. We don't care like what particular path or anything like that. We can modify the board however we want. So yeah, there's a follow-up. How can you use search pruning to make your solution faster with a larger board? My guess is that every time you I don't know search pruning per se, but another optimization you can do is you can have another save. You can save the state of like at a particular index. Like if you are at let's say for this, let's say we're going reverse order where you have this E here, you can see if this is an index in the word C, and then try to find, okay, is this S E E, and you save at this point, okay, this I'm able to find a valid path from index 1, right? And then once you go to here and you find here, all you can do is, okay, if this has already done the search, if this is at index 1 and this is at index 0, that's done. We found it, right? We don't have to do another. If we do EE and do S and then EE, that's redundant work, right? We're doing overlap. So you can check out every index, at every cell, if that is a subset of the word, right? I think with that, that's pretty much it. See you guys tomorrow.